Good evening, all. This is the test review answer key to hopefully give you a good expectation on what the test will hold for tomorrow and how to do every question. So if you notice, I've already written out the molar masses for both lithium oxide and for lithium. The test, you will not have to figure out any molar masses. They will all be given to you already. So let's go ahead and dive in without any hesitation. Note, we want to go ahead and read the instructions. Always read the instructions. They're not there just to add decoration. They do give insight. Notice the question is, use the following balanced chemical equation to answer questions 1 and 2. Write the letter that corresponds to the correct answer in the blank provided. And then we have our balanced chemical equation. Note, question number 1. Says, if 54.5 grams of lithium are used in this reaction, how many moles of lithium oxide are produced? What do we put on our first railroad? We put what we're given, 54.5 grams of lithium. What are we going to turn it into ultimately at the very end? We'll turn it into moles of lithium oxide. So our end game is going to be moles of lithium oxide. So we're going to go from grams of lithium to moles of lithium. This is our main game plan. To I didn't specify what compound. My bad. Moles of lithium. Notice, why is that a problem? If I don't specify the compound, I'm going to get really confused. Writing everything out really helps us out. So grams to moles to moles. Grams of lithium to moles of lithium to moles of lithium oxide. That's our game plan. So let's go ahead and show that process. We start with 54.5 grams of lithium. We need to turn grams into moles first, right? So remember, what goes in the bottom has to be the exact same units. Exact same units. Exact same units. Has to be the exact same units. If these are not identical, you're wrong. Okay? Have to be the exact same units. Then we're turning grams into moles. And then what has to go on the bottom of the next railroad? Exact same units, moles of lithium. Remember, in a mole to gram conversion, what number goes beside moles? Always 1. And our molar mass for lithium is 6.94. That was given to us, and it's also on the diagram. Then, how do we know what numbers goes beside a mole to mole conversion? Well, we look at the balanced chemical equation. 4 is beside lithium, and 2 is beside lithium oxide. Grams of lithium cancel out, moles of lithium cancel out, leaving us only with moles of lithium oxide. So let's go ahead and plug in these numbers. Ready? 54.5 times 2 divided by 6.94 times 4. And my answer is 3.93 moles of lithium oxide. I showed my work. I got the 5 points. I'm going to write my answer, B. Next. Using the same problem, because remember this is for questions 1 and 2, the same exact balanced chemical equation. How many grams of oxygen are needed to produce 104 grams of lithium oxide? So we're going to put what we're given, our first railroad, 104 grams of lithium oxide. So we're going to go from grams of lithium oxide to what? What's our ultimate end goal? Grams of oxygen. That's what we're trying to figure out, grams of oxygen. What do we have to turn grams of lithium oxide into first? Hopefully you said moles of lithium oxide. And then can we turn moles of lithium oxide into grams of oxygen? No, we have to turn moles of lithium oxide to moles of oxygen. This is like our information highway, our bridge in going from one compound to another. We can't do anything else if we don't do that mole to mole bridge. Then we'll do moles to oxygen. Moles to grams. So our first step. Grams goes in the bottom. Has to be identical, right? The diagonal. So grams of lithium to moles of lithium oxide, Then moles of lithium oxide to moles of what? Moles of oxygen. And then moles of oxygen to grams of oxygen. Let's fill in these numbers, ready? How many moles are in the... I said the wrong word. In a mole to gram conversion, what number goes beside moles? Always 1. we have the molar mass for lithium oxide. It's up here, so I'm going to go ahead and bring that down. It's our molar mass, so that's 29.88. Then we look at our balanced equation to get those coefficients. The number beside oxygen is 1, and our number beside lithium oxide is 2. Now we're back to a mole to gram conversion. What number goes beside moles? 1. How many grams are there in the molar mass of oxygen gas? Well, oxygen's atomic mass is 16, and since there's 2 of them, 16 times 2 is 32.00 grams. We have our setup. Let's go ahead and calculate. I'm going to say 104 times 32 equals, and then I'm going to divide that by 29.88 times 2. By the way, I do that in parentheses to keep everything compact. If you know how to use your calculator really fluently, that'll be very helpful. And that gives us 55.7 grams of oxygen gas. Note, you want to show your answer right here to get full credit. If you don't show me your work and if you don't show me your final answer in the process of getting there, I can't give you those 5 points. These 5 points are to make sure that you actually did the problem correctly. Each question is going to be worth 10 points. Every question on multiple choice is 10. The showing your work is 5. All right, next one. I'll move this up here. The number 3 has nothing to do with questions 1 and 2. This is an independent question. It says phosphoric acid reacts with an excess of aluminum sulfate to produce aluminum phosphate and sulfuric acid. By the way, those were a lot of words, right? We don't need any of them for this question. No, let's read the rest of it. Don't let your brain get so defeated. Read the rest of it. Persevere. Ready? Starting at if. If you calculate a theoretical yield of 53 liters of sulfuric acid at STP, standard temperature and pressure, but 32.5 liters of sulfuric acid is actually produced in the experiment, what is your percent yield? Do you remember the formula for percent yield? It's going to be percent yield equals actual yield divided by the theoretical yield. Do we have values for each of these quantities? Absolutely we do. What is our actual? Our actual yield was 32.5. That's what we actually produced, our actual yield. When we say yield, it means how much of our product. So 32.5 liters of sulfuric acid, H2SO4. What was our theoretical? Well, normally we calculate it, but in this case, it was given to us. So 53 liters, what do we do between these two numbers? We'll divide 32.5 divided by 53 equals 61 point, excuse me, my brain is working ahead. 0.61320075, and it keeps going, right? But note, what is the actual formula? Once we get that quotient, actual divided by theoretical, we have to multiply it by 100. If we don't multiply it by 100, we're left as a decimal. But when we multiply by 100, it turns the decimal into a what? Percent. So multiply by 100, moves the decimal 2 places to the right. So our answer is 61.3%, or 32%. D. All right, next question. Let me go ahead and get to there. Our next page, rather. Okay. Will it go? Whoop. There it is. All right, let's read the instructions. Use the following balanced chemical equation and molar masses to answer questions 4 through 7. So here's our balanced equation. And there are some molar masses that are given to us, so we don't have to calculate, because it does kind of take a lot of time to get those molar masses, right? So I've given them all to you. If this reaction starts with 27.0 grams of silver nitrate and 43.5 grams of iron chloride, which compound is the limiting reactant? In these cases, remember, the key phrase is you want to turn each of your givens to the other reactant. You want to turn what you're given into the units of your other reactant. Notice how many givens do we start with? 2. We We start with two different givens. And both of these, what do they both have in common? They are both reactants, right? They're both reactants. We need to figure out which one's our limiting and which one is our excess. So in order to do this, we have to go ahead and convert each one individually into the same unit of the other reactant. So we start with 27.0 grams of silver nitrate. And we're going to turn that into grams of our other reactant, which in this case is going to be iron 3 chloride. That's our end goal, FeCl3. Let's fill in the gaps. Ready? Diagonal. Keep it diagonal. How do we know what goes on the bottom? It has to be the exact same units. So grams of silver nitrate turn first into moles of silver nitrate. We can't go anywhere else if we don't go to the mole. Then mole of silver nitrate. Just remember, these have to be diagonal. Some of you are not making them diagonal. If you don't do it, it's going to mess your equation up. We're turning moles of silver nitrate into moles of iron 3 chloride. And we're turning moles of iron 3 chloride into grams of iron 3 chloride. What number goes beside moles in any conversion like that, where it's going from moles to grams or grams to moles? 1 always goes beside moles. What number goes beside grams in a mole to gram conversion? Well, you're going to look at the molar mass. Here's the molar mass for silver nitrate, 169.88. Then, how do we know what numbers go beside these mole to mole conversions? Well, we're going to do the coefficients from our Gauss equation, right? So 3 is going to go beside silver nitrate, and, oh, wrong one. 1 is going to go beside iron 3 chloride. What number is going to go beside the grams? Well, of course, we're just going to use the molar mass, which is given to us 162.0.20 grams. Okay, let's go ahead and calculate that. It's going to give us 27 times 162.2. I'm going to divide that by the product of 169.88 times 3. That'll give us 8.59. That's where I'm going to stop because we had 3 sig figs at the given. 8.59 grams of FeCl3. I'm running out of space. FeCl3. I know that unit because that's my last one, right? The grams of silver nitrate canceled, moles of silver nitrate canceled, moles of iron 3 chloride canceled, leaving us only with grams. Now I'm going to do it for the other given. 43.5 grams of FeCl3 times, and we're going to convert that into grams of our other reactant. In this case, it's silver nitrate. Convert grams into what first? Moles. FeCl3. And convert moles into moles. Moles of iron 3 chloride to moles of silver nitrate. That's our other reactant. Then moles of silver nitrate into grams of silver nitrate. 1 goes beside the moles in a mole to gram conversion. Our molar mass will go beside the iron 3 chloride, which in this case, again, is 162.2 grams. That's given to us. It'll be given to you on the test. Mole to mole conversion, we look at the coefficients, right? Our coefficient for iron 3 chloride is 1. That's given to us in the balance equation. And then for silver nitrate, that's 3. And then for grams of silver nitrate, again, we look at the molar mass, and that's 169.88 grams per mole. Let's go ahead and multiply these. 43.5 times 3 times 169.88 divided by, all of that divided by 162.2. That's going to give us 100. Oh, I turned off my pen. 136.6. That's just going to round to 137 because we want 3 sig figs. Grams of silver nitrate. Okay, our next step is I'm going to write the word need above this column. As in, these represent how much of that substance I need for the reaction. This represents how much I have. When I write these words down, it helps my brain to really visualize what I'm working with. If I don't write those words down, I can get really confused really fast. Even me, right? So, if an experienced chemist, I don't know if I call myself a chemist, but someone with more experience, if they need to have these things written down, then I recommend doing that yourself to help your brain visualize everything. If you can do it on your head without getting confused, more power to you. Okay, so notice I drew these crossroads, or these little split arrows, to show that this is representing grams of iron through chloride. This is showing grams of silver nitrate. I'm going to go ahead and erase a lot of those things so we don't get as confused. Okay. The amount of silver nitrate that I have is 27, but how much do I need? I need a whole lot more. It is okay. I think I misspoke in class the other day. I said it needs to be like within 30 grams or so. It can, in certain situations, be pretty substantially different like this. That can happen. We might just have a really meager supply. So don't let that be confusing to you. Don't let that throw you off. I think I was just so used to the problem yesterday or the day before that I knew that was not the right answer. So looking at this, we need a lot more than what we have. We need 137, but when we only have 27. So we're like 110 grams shy of what we need. So what does that mean that silver nitrate is? That's our limiting reactant. Because we need much more than what we have. We don't have enough. Next, this should be our excess, but let's look at it. We need 8.59 grams. That's almost 9 grams. But we have 44 grams. Whoa, we have a lot more. We have a lot more than what we need. So if we have a lot more than what we need, what do we call that? We call that our excess reactant. Okay, so let's answer the question. Number 4. If this reaction starts with 27, which compound is a limiting reactant? Which one is it? Silver nitrate, A. Question 5 goes along with the work we just did. How many grams of the excess reactant will remain after this reaction? So what was our excess reactant? It was iron 3 chloride. And we want to figure out how many grams we're left with. So we're going to do 43.5 grams. Again, this is our excess reactant. We're trying to figure out how much will be left, so we'll subtract the two values. How much we have minus how much we need. Minus 8.59 grams of iron 3 chloride. And that gives us, drum roll, brrr, B, 34.9 grams of iron 3 chloride. So now that we've solved that, let me go back. Where are we going? Nope, let's go back. Nope, that one. Here we are. Yep, nope. Slide over. Okay. Now that we've gotten our limiting reactant and our excess reactant, let's go ahead and answer number 6. It says using your limiting reactant, which is what? Silver nitrate. That's our limiting reactant. Using your limiting reactant as the starting amount given, calculate the amount of grams of silver chloride that can be produced. So we're going to start with our limiting reactant. How much do we have of our limiting reactants? How much do we have of silver nitrate? We're going to look all the way back at the beginning of question 4. This reaction starts with 27 grams of silver nitrate. And what was silver nitrate? Silver nitrate's our limiting reactants. So that's how much we're starting with. 27 grams of silver nitrate. Times. What are we converting what are we converting our limiting reactants into? Well, it's our standard, it's our basis on converting to grams of silver chloride of one of our products. So we're going to want to finish with grams of silver chloride. Let's go ahead and do the process. Ready? So grams of silver nitrate go on the bottom. It's diagonal. I'm going to convert that into moles, right? We can't turn anything else into anything if it's not a mole. A mole of silver nitrate. This might feel repetitive, but if you don't follow this method, it might lead you into dangerous waters of error. And moles of silver chloride into grams of silver chloride. Note our numbers. 1 goes beside moles whenever it's a mole to gram conversion. We're going to use the molar masses given to us at the very beginning, up here, right? Here's all of our molar masses. For silver nitrate, again, it's 169.88 is given to us. For moles of silver nitrate and moles of silver chloride, we look at the balanced chemical equation. For silver nitrate, that's 3. For silver chloride, that's 3. And then right here, we got 1 mole to silver chloride to how many grams of silver chloride? Well, the molar mass of silver chloride is also given to us, 143.32. Note, I can go ahead and if you notice this, some of you may have noticed this, some of you may have not. It's 3 to 3, so what can we do with those? We could technically just cancel those. So that just becomes 1 and 1. That's a minor step, but it's one that you can take if you want to go ahead and just not use 3s in your multiplication. But if you want to and just keep everything consistent, then feel free. So 27 times 143.32 divided by 169.88. That equals 22.77, or to round to 3 sig figs, 22.8 grams of silver chloride. Grams of silver chloride. I don't know, I'm working with grams of silver chloride, but grams of silver nitrate canceled, moles of silver nitrate canceled, moles of silver chloride canceled. That leaves us with grams of silver chloride. Last question before the big bonus. Using the theoretical yield calculated from question number 6, so there's our theoretical yield. If everything went right, that's the number we get. Using our theoretical yield calculated from question number 6, calculate the percent yield if the actual yield was 15.276. What is the formula for percent yield? It should be actual, which in this case is 15.276 grams of silver chloride, divided by theoretical, which, where do we get the theoretical? From our calculation. 22.8 grams of silver chloride. I'm going to multiply all of that by 100 to turn it into percent. So 15.276 divided by 22.8 multiplied by 100 gives us 67%. 2 numbers in succession. That's completely fine, right? It's just a number. Can't hurt you. That, if you know how to do everything I just went over, you will crush the test in a good way. You're welcome to pause the video now or stop the video if you want to. But if you're interested in possibly getting this 100-point bonus question, here's how you do it. In a single replacement reaction, and by the way, your answer must be 100% accurate, has to have the correct number of sig figs, the correct units, everything, to receive full credit. If you say only did this question and left the rest of the test blank, I'm tempted to give you a 50 max if some of these things are wrong. But if you get everything completely right, then it's an immediate 100. The test will cap at 106. The test will cap at 106. Okay. In a single replacement reaction, aluminum, so I'm going to go ahead and start writing out my balanced equation. Aluminum reacts with sulfuric acid, H2SO4. That's all it tells us. We don't know the products, right? We can infer what one of the products is, right? One of the products is going to be hydrogen gas. But just in case you don't have that intuition, a single replacement is going to take our cations and swap them. So now, instead of aluminum being by itself, what's now by itself? Our other cation, which in this case is hydrogen. So hydrogen is now by itself. And it needs a subscript 2 because it's diatomic. And now, is aluminum by itself? No, it is now with sulfate. Oh, wrong letter. It is now with sulfate. Al2SO4 3 is aluminum sulfate. How did I get those subscripts? Well, just for a quick reminder, aluminum has a +3 charge, sulfate has a -2 charge according to your cation polyatomic ion chart. Each element's charge becomes the other element's subscript, and that gives us those subscripts. Cool? Yes, Mr. Allen, very cool. Then, our first step is to go ahead and split left side from right side. We got aluminum, we got hydrogen, we got sulfate on both sides, so we can do that, right? Sulfate on the left, sulfate on the right. we got aluminum. We're going to do it in the same order. Aluminum, hydrogen, and sulfate. We're currently starting with 1 aluminum, 2 hydrogens, and 1 sulfate. Starting over here with 2 aluminums, 2 hydrogens, and 3 sulfates. What's our first thing to balance? Always the metals. So let's go ahead and try that. I'm going to multiply aluminum by 2, and that 2 represents the coefficient. Then we're going to look at our hydrogens. Hydrogens are currently balanced. Well, actually, we should chronologically go to sulfates first, right? We go metals, nonmetals, hydrogen, then oxygen. So let's go to sulfate. What should we multiply sulfate on the reactant side by to make it equal to 3? Good. We'll multiply by 3. And what does that 3 represent? The coefficient. That 3 doesn't just hit the whole sulfate group. It also hits the what? Hydrogen. So we have to multiply that by 3. Is everything balanced? Aluminums? Good. Sulfates? Good. Hydrogens? No. But easy fix. Ready? What can we multiply 2 by to make it equal to 6? Multiply by 3. What does that 3 represent? Represents our coefficient. Is everything now balanced? Yes. So that's our balanced equation. So let's get some room out. Clear this out of the way. Okay, here we go. The question says, when 112.4 grams of aluminum is reacted with 74.5 grams of sulfuric acid, what volume in liters of hydrogen gas will be produced at standard temperature and pressure? And then it asks about percent yield, but we'll get there first, or we'll get there later. We have to first identify what our limiting reactants is. If we're given 2 givens of our reactants, and then we're asking what volume of a product will be formed, we aren't going to use both of these givens. We need to take these givens and turn them into a limiting reactant. We need to identify which one of our reactants is going to keep this whole reaction from taking place to completion. Which one is going to limit us? The one that limits us will determine which one we will stoichiometrically convert into liters of hydrogen gas. So let's go ahead and do that. Ready? Let's convert 112.4 grams of aluminum into grams of the other reactant. Remember, we take each of our givens and turn it into grams of the other reactant. So we're going to say grams of aluminum, moles of aluminum, moles of aluminum, into, what's the other reactant? Moles of sulfuric acid, H2SO4. Then moles of H2SO4 turns into grams of H2SO4. Go ahead and plug in those numbers. We're going to go quickly through this. 1. Our coefficients are 2 and 3. Grams of aluminum. Aluminum's molar mass. Table in front of me. Aluminum's molar mass. Walking over to my periodic table in my classroom is 26.98. Then sulfuric acid's molar mass is, hey Siri, what's the molar mass of sulfuric acid? 97.97 grams. 97.97 grams. After that, we'll go ahead and convert this into the grams of sulfuric acid. So once we do that, it's going to be 112.4 times 3 times 97.97 divided by the product of 26.98 times 2. That should give us 612. Let me write it actually down here. 612.2 grams of sulfuric acid. Then we'll start with the other reactant, and that's 74.5 grams of sulfuric acid is going to convert all the way into grams of aluminum. I'm taking the grams of one reactant and turning it into grams of the other. So 74 grams of sulfuric acid, let's go ahead and convert that into grams of moles of sulfuric acid. Moles of sulfuric acid. Turn moles of sulfuric acid into moles of aluminum. Now we're going to turn moles of aluminum into grams of aluminum. Remember, grams of sulfuric acid, is 97.97 grams according to Siri. We could calculate that, but I didn't have enough hands on me. That's 1 mole for every gram, right? We put the 1 beside the mole. And how many moles of sulfuric acid times or per moles of aluminum? Well, according to our balanced equation, that's 2 for aluminum and 3 for sulfuric acid. 1 mole for aluminum and grams of aluminum will be 26.98. That's the molar mass of aluminum. Go ahead and plug in those numbers. That'll be 74.5 times 2. Times 2 times 26.98 divided by the product of 97.97 times 3. And that should give us equals 13.67 grams. Now we will go ahead and round that to 13.7 to stay consistent with sig figs. That's grams of aluminum because everything else canceled out. Okay, so what does this column over here represent? That column represents how much we need, right? This column represents how much we have. So which one's our limiting reactants? Well, we need 13 grams, or about 14 grams of aluminum, but we actually have 112. So that's an excess. That's our excess reactants. Let's look at the other one. We have 74.5 grams of sulfuric acid, but we need, we need 612.2 grams of sulfuric acid. We need to go to the store and get some more sulfuric acid. So our limiting reactant is going to be sulfuric acid. That is super important because that determines what we do next. Ready? Here's our last step, kind of. We'll then need to go ahead and turn this into liters of hydrogen gas. That's what the question's asking for. What volume in liters of hydrogen gas will be produced? So here we go. Ready? On our first railroad, we're going to convert 74.5 grams of sulfuric acid. That's our limiting reactant. I can convert it all the way into liters of what? Of hydrogen gas. That test tube. Let's go ahead and make our way there. Grams of sulfuric acid becomes what? Moles of sulfuric acid. Moles of sulfuric acid becomes what? Liters of hydrogen, right? No. Those are completely 2 different compounds. Do you see this? The only way, that kind of looks like a flex. The only way that we can actually have 2 different molecules in the same railroad is if it's a mole-to-mole conversion. Nothing else will work. Okay? Capiche? Then moles of hydrogen will then be turned into liters of hydrogen. Let's fill in these numbers. Ready? 1 always goes beside mole in a mole to something conversion. In this case, a mole to gram or a mole to liter. The grams of sulfuric acid, as we calculated up here, is 97.97. The coefficients for hydrogen are 3. The coefficient for sulfuric acid is also 3. So that means that's going to be able to cancel out easily. Then right here, we need to solve for hydrogen's molar mass, right? Wrong. But why, Mr. Wrong? Why did I not just solve for hydrogen's molar mass? Is this molar mass? No, this is molar volume. Is there a fixed constant that we use when doing a molar volume? Yes! 22.4 liters per mole. Now we're ready. Are you ready? We're ready. We're going to do 74.5. And by the way, I'm going to go ahead and cancel out those 3s. It just makes our life a little easier. Very little easier, but makes our life easier. 74.5 times 22.4 gives us 1668.8. Divide by 97.97. That gives us 17 point... Let me do my sig figs right. 17.03. So we're going to say 17.0 because we had 3 sig figs at the beginning. So we're going to end with 3 sig figs at the end. 17.0, what's our unit? Our unit is liters of hydrogen. That's our units, or that's our theoretical yield, isn't it? Based upon our limiting reactants, we would get 17.0 liters of hydrogen at STP, at standard temperature and pressure. Now, did that answer the whole question? No, let's go back. Ready? If the actual yield was 9.44 liters, what is percent yield? What did that just give us? And what do we want to solve? The percent. Percent yield equals the actual divided by the theoretical. Our actual given to us, 9.44. The theoretical, which we just calculated based upon our limiting reactants, which we had to solve, is 17.0. What do we do? Well, actually, before we do that, multiply by 100. 9.44. We're in the finish line. Ready? 17 divided by 17 equals 0.55. Let me go ahead and multiply that by 100. That equals 55.5%. That is our percent yield. That is how much we produced. There's our answer. So, that is the test review. Expect the test tomorrow to look very, very similar, just with completely different questions. And by completely different, I mean different numbers, different balanced equations. All the molar mass is already calculated for you. You won't have to balance anything. You won't have to name anything, unless you want to try the big kahuna. Which, that wasn't that bad, was it? I think the biggest thing would just make sure that you know how to name those things and balance them correctly. Because if we don't name those things correctly, if we don't balance them correctly, what happens? We get it all wrong. Say this was 2. Say you put 2 instead of 3. Would that mess up things? Yeah, look at that. That would become 2. That would become 2. That would become 2. It would mess up a lot of things. So that's why this is worth 100 points, because you have to be exactly right, or it all messes up. May those who attempt it find bravery. Okay. Email me, message me with any questions, and I'll be glad to help. Fare thee well.